So we're very fortunate today to have such a renowned speaker here for a bonus session in our seminar series, which, by the way, this is a joint seminar between the AIMSEC Institute and the Heinz College and the AI Institute for Societal Decision Making. And today we have Gopal Ramchurn with us, who's a professor of artificial intelligence, a Turing Fellow, and a Fellow of the Institution of Engineering and Technology. So he's coming to us from the University of Southampton in the UK. He's also the CEO of the Responsible AI UK, director of the UKRI Trustworthy Autonomous Systems Hub as well. So involved in a number of areas, but today's talk looks like it focuses on emerging challenges in responsible and trustworthy AI. So Gopal.
Thanks, Sean. And it's exciting to be here today. It's I think 14 years since, or 13 years since I've been to CMU, and I'm very grateful for the opportunity to talk to you a bit about my work in agents, multi-agent systems, trustworthy AI, but also the program that I run called Responsible AI UK, and some of the emerging challenges I'm seeing as part of the work that I'm doing with the UK government and other organizations across the world. So this talk is in 4 parts. Hopefully we'll cover at least 3 of those parts. I don't want to drag it on too much, and feel free to interrupt me during the talk if you have any questions. Some of it will be more technical, some of it will be more about my program, my risk program, and some of it about emerging challenges and provocations I have for you. And maybe we can have a chat about some of these provocations as we go. So I'm a professor of AI, but most of my work has been in multi-agent systems. So I started did my PhD in multi-agent negotiation, really saw the evolution of the field from agent-based systems to multi-agent systems to human-machine teaming systems over the last 20 years. And we're doing great work in the 2019, 2018, and then COVID hit. And it was much harder to do more work in human-machine teaming when you could not access the humans. But still, we did some work in that space online, and I was fortunate enough, building on the work that I'd done over the last 20 years, to win some big grants. As Noah mentioned, I'm a former director of the UKRI Trustworthy Autonomous Systems Hub, and currently CEO of Responsible AI UK, which is a large research program, funding program in the UK. I'll give you some more details on that in a bit. So part 1, from agents to human agent collectives to trustworthy human AI partnerships. So I'm from the generation of researchers that understood agents to be bits of software that are autonomous, that are proactive, social, that were well defined in those terms. And we did a lot of work back in the days from the 1990s to late 2000s, and still this community is very, very, very active. And Anand here is one of the founders of this field and working on BDI agents, if you remember that work. I had a couple of slides to explain what agents are, but I'm hoping that the audience here knows what agents are about. And because that's significant questions these days. And just yesterday we were at the Brookings Institution in Washington, DC, talking about what is an agentic AI system, right? What's an agentic system? And many questions about the capabilities of agents have been thought through over the last 20 years by the multi-agent systems community. And we had some of these research areas covered. We already thought about agent-based argumentation, when we'll have agents chatting to each other, arguing with each other, agreeing on deals, etc. We were thinking about mechanisms to manage multi-agent systems. So how do you cope with a system where agents can come in and out, go out of the environment at any point in time, and build a number of electronic institutions, normative systems, game theoretic mechanisms to manage all these agentic behaviors. We also worried about trust. There's a few significant questions about trust in agents, but also in humans from agents, and teaming algorithms, multi-agent coordination algorithms. And a lot of my work in the beginning was about trying to demonstrate that these multi-agent systems would have an impact in the real world. So a lot of my work initially worked on simulators like RoboCup Rescue. Maybe you've heard of it. If you're part of the RoboCup community, Manuela Veloso here is very active in that community. I mean, I don't know if she's still around, but she's very much one of those leaders who helped create that field of human machine teaming and multi-robot systems. So the work then involved building agents that would simulate human behaviors, simulate teams of individual humans. And we developed a number of algorithms to optimize the allocation of tasks across these teams. We model humans. For example, we have here different maps of different cities. So we had Kobe, we had Foligno in Italy, the cities in Japan, in Turkey, etc., etc. We modeled those infrastructure. 3D models was not that sophisticated at the time. Now we can do much better. We modeled casualties, people dying in buildings because of an earthquake. Don't know if you know the scenario of Robocop rescue simulation, but an earthquake has hit the city, fire spread, people are trapped, roads are blocked, and you need to clear the whole space. So these colors show you where the casualties are, where the civilians are. The police is blue, the red dots are fire trucks, and we had to build algorithms to optimize where ambulances go to pick up the casualties because they were going to die. The black dots are the dead humans there, etc., etc. So all of this was modeled, and we won awards for the work we did on modeling the real world, build realistic simulations of fire spreading across the city. We modeled building material. We modeled human life decay, and it was really interesting work. But will this work with real humans, right? And we have similar questions these days about testing GPT and LLM systems that need to interact with humans. And very often we simulate humans, and that's what we were doing back in the days. And I was not happy with that. And it's not just in this scenario that we looked at this. We looked at other scenarios more, much closer to what you can see right now with agentic systems, agents that, for example, could optimize your batteries or advise you on your energy tariff. So this is a model we built, late 2000s, of a smart home with a certain load profile, so certain energy demand, and equipped with a battery that could store energy when the price on the grid is low, and then give you back that energy when it's high. And we modeled all of that using all these equations, and then looked at how we model humans using the home. So this load profile that you see there was drawn from a distribution that we constructed out of data sets of the grid and modeled like 26 million homes in the UK. Did amazing work on simulating human behaviors again, using large data sets that are quite sort of consistent, right? You have, for example, in the UK, you have 7 typical profiles of consumption: people coming in at a certain time, coming online at a certain time, going offline at a certain time, etc. So it's quite a good model to work with, and a good data set to work with to model human behavior. But you took out, and it worked quite well when you look at static behaviors, and what you were playing with was a battery. But what if the users could change their behavior or were incentivized to shift appliances around? And we also tried to model that. You would get here, we modeled people shifting appliances around to take advantage of the cheap prices on the grid. And you get significant spikes when you apply real-time pricing versus time of use pricing, versus a learning-based algorithm that we designed. So the algorithm would behave like a human and learn to react to certain prices on behalf of the human in this case. But it was not. It was not. It didn't give us much satisfaction, because when you expose humans to prices, they may ignore it, they may react to it, they may not be happy with an agent that shifts their appliances around, they may not be happy with the performance of the agent if it's not clear whether the agent is saving them any money, right? So all of that told us that we need to do better at making these systems work with humans, getting agents, AI to work with humans. So we came up with this. We won this grant to run this project on human agent collectives, the ORCID program. It was a £10 million program that started in 2010 and lasted till 2016. involved a number of emergency response agencies, defense companies, energy companies as well, and looked at defining what the fundamental elements of these human agent teams or human agent collectives. Sometimes they may not work as a team, right? They may be just a collective of humans and machines that need to be interacting with each other. For example, people buying and selling stuff to each other. And we defined dimensions of this. I'm going to play the video here. The following dimensions of this. Ooh. Okay. Right. Of these human agent collectives. So fundamental principles underlying these collectives are notions of flexible autonomy. Flexible autonomy where it's not just about adjusting the level of autonomy of an AI system. It's about it's that plus the idea that the agent could be in control of the human, could be guiding the human to do certain things. So that's the notion of flexible autonomy that we thought about and build models for. The second dimension was agile teaming. So thinking about how teams of humans and machines form, disband, and reform, depending on the environmental changes, depending on the needs of the agents and the humans in the real world. The third element was incentive engineering. So how do we engineer incentives in a system to make sure that both humans and agents behave in a way that would maximize social welfare? And finally,
we are studying systems that involve.
Sorry, that was me about 10 years ago. And the last point here is about the accountable information infrastructure. When you have teams of humans and machines working together, understanding who is responsible when things go wrong is really, really important. Who made the decision? Who generated the data that led to a failure or to the success of the team? The building an accountable information infrastructure, tracking the provenance of these humans and machines.
We are studying systems.
It's using timings here. Sorry about that. Don't know if I can turn that off. I don't need to turn that off. Okay. So, yeah, I was talking about an accountable information infrastructure is really important if you want to have a team of humans and machines that you can trust, that remains accountable for its decisions, and you need to be able to manage all of that data in an automated fashion. And we built a number of solutions to that, published lots of papers, and one of the key outputs was the W3C provenance tracking standard, which is a W3C standard to track the generation, processing of data by agents and humans on the web. So that's a standard you can download and reuse in many applications. But give you an example of what human agent collectives look like in the real world. I've got two examples. And we build these applications and the core algorithms underlying some of these applications within that project. And I can recommend some of these papers to you if you're interested. So looking at a scenario, again, a disaster response scenario, similar to what I presented earlier, but this time we have real humans in the loop. We have humans involved in classifying and summarizing reports online on social media, not just human, but using human intelligence, but also machine intelligence. How do you combine human and machine intelligence to classify those reports? We build a platform for that. An example of such teaming was demonstrated in the Ushahidi platform. If you want to go back in history and check that platform out, but was used in the Kenyan elections to track violence. It was used in Haiti to track casualties or events across a disaster space during the Haiti or in the aftermath of the Haiti earthquake. And we built algorithms to improve the performance of the team using machine learning, using a number of interfaces that would help us ensure that we can trust both the humans and the machines. So typically the problem is that if you ask humans and machines to classify data, both the humans and the machines can fail. How do you trust? How do you make sure you get the best outcome, factoring in the uncertainty around the human decision-making and the machine decision-making? We also build algorithms to optimize the allocation of UAVs, so drones, to do a survey of the area, and actually deploy these drones alongside humans to make the best use of both human intelligence on the ground, people moving on the ground, gathering data on the ground, but drones that have capture the aerial view. So these algorithms would also incorporate some level of machine autonomy. So you would have UAVs that can fly on their own and tasks, react to certain task requests from humans. And the goal there was to be able to fly maybe 3 drones with 1 pilot. And we managed to do that. And on that side, so that's another OODA loop. If you're familiar with OODA loops, so another decision-making loop, an action loop. Once you've surveyed the area with drones and with humans on the ground, you can create tasks for the emergency responders to go and save the casualties in the real world. And again, we use an algorithm to optimize the allocation of humans to those tasks. And I'll show you the kind of challenge we then faced when we deployed teams of humans to undertake similar tasks to what I showed you in the simulation earlier. In the simulation that you saw earlier, the pictures at least you saw earlier, you would task the police agents or the ambulance agents to just go and do these tasks. When you try and do that with real humans, you get a very different response. They don't always do what you want them to do. And that's what human agent collectives, sort of research in human agent collectives allows us to surface. And obviously, I've mentioned the provenance of decisions and information that was tracked across the whole system. So yeah, this is an example of what we mean by human agent collectives in a number of settings. And nowadays, we are talking about LLM agents that will probably do some of these tasks with humans. And the fundamental construct we've built over the last few years will probably help us deploy these systems more effectively. Another area I mentioned energy systems, I mentioned energy storage. We built a number of human agent collectives for smart energy systems, looking at both homes and the grid level optimization. So look at neighborhood energy management, electric vehicles, etc., etc. But really try to figure out how humans would react to these systems, not just simulating the human. So we built, and actually the paper, the first paper we wrote on this, the figure energy, was presented here at UBComp 2012, I think, at CMU, which was basically an agent figuring out on the background what appliances you're running in your home and presenting that information back to you. And you could manipulate that information. You could play around with that information to figure out how much energy you would save. You can imagine similar agents being built now to do this for you, right? Using GPT and others. But it was really important, and that's what we learned with this experiment, was really important to give humans control, humans ways of interfacing with that data in a way that's meaningful to them. So what you see on the picture here, a bunch of boxes, right, that represent the amount of energy that each appliance is consuming. And you could play around with these boxes to try and meet an energy target. So still making sure, and that's what we tend to lose when we just simulate humans. You don't see that reaction of humans, and you don't get humans to learn better behaviors unless you give them control. A bunch of other algorithms and platforms we built. Smart Thermal was a real smart thermostat, a bit like the Nest, but better than the Nest, we would say, where in a way that in that it would react to real-time prices and would help you, it would learn your preferences for comfort versus cost, and we would study those systems. And we studied them both quantitatively and qualitatively, right? So we would measure the performance of these systems, we'll measure how humans react to these systems, whether these systems actually improve their lives, improve their savings, and whether they accepted those systems. So it's just a few videos, pictures of some of the systems we deployed. So I mentioned, we'll come back to that in a second. So that needs to come later. Okay. So that was the end of the project. We were wondering why people didn't trust this system sometimes, because and I'll give you an example of how we fixed that in one of these disaster response systems. We were wondering whether humans needed to have some measure of confidence declared by these agents. This was 2016. We didn't have ChatGPT then. I think if we had to rerun this experiment, we would use an LLM to do it. And interestingly, I went back to this paper when people started asking me, how do we evaluate these agents? So how should we build human-machine partnerships with these sorts of new agents? And this study talks about transcription agent, an agent that would look at images and transcribe it, which you can now do easily. We had to fake the whole thing back then. It was the proper Wizard of Oz type study. So we faked the agent behaviors. We faked the text that people had to look at, etc. And basically, there are two tasks in this experiment. One task is a manual task that a human has to do, and it involves correcting grammatical errors. The other task is a task that the agent is doing. So the agent is transcribing Filipino text, handwritten Filipino text. You can't see the text unless you click that button. So it's ongoing in the background. It takes 30 seconds for the agent to do one task at a time. It's running an OCR algorithm now, faster, obviously. But the agent is doing this task next to you, and you're working on your thing, and it's doing its stuff, and you're under time pressure to complete as many tasks as you can. So you get a document, you need to correct all the mistakes. The agent is doing its task, and you need to watch whether the agent is happy with its output. So the agent can tell you whether it has high or low confidence in its output. Okay. I guess everyone here has used GPT. Have you ever seen GPT tell you how confident it is in its output? Never, right? Can you guess why it doesn't do that? Why don't they tell you how confident they are in their outputs? Any thoughts? This study gives you an idea why. Yes? No?
I was just saying, maybe they don't know.
Well, maybe they don't know, but even if they did know, and they would not want to show it to you because it could undermine your trust in the system, right? If it's generating lots of outputs that with confidence 0.1, 10 times, would you keep using it? Probably turn it off, right? So this experiment aimed to surface, whether people, if they have an understanding of the confidence that the agent has in its output, whether they would do more tasks or not. And it turns out they do. I mean, we'll see the results in a second. They were under time pressure to complete all these tasks. They were getting financial rewards of different types. You can check out the paper, but different rewards for the agent doing lots of tasks from the human doing lots of tasks. And we played around with these rewards, very much in the style of behavioral economics type studies, to see whether humans wanted to do more challenging tasks or wanted more money, whether the incentives really worked for them. So these are the hypotheses we put down when we ran these experiments. And obviously, you would hope that if the agent has high confidence in certain tasks, instead of checking that work, they would just accept that the agent has done the job, right? They see the review button come up, and they say, just click it. I don't have time to do this. Let me do as many tasks as I can. I'm not going to do much detail, but these are some of the results that we got from the experiment. So we find, obviously, that with the display of confidence, you could get more tasks in this particular setting. I'm not saying in a general open setting, but in this particular setting, the humans would accept lots of blindly, lots of these tasks. We could measure this very accurately. But even if they did that, confidence information did not actually influence overall performance. So people who had the confidence information performed as well as those who didn't have the confidence information in these agents. So they got lots of tasks done in equal measure, whether they had this confidence information or not. And the one thing that I went back to in that paper was these results from the interviews. So those people who were getting that confidence information could accept all these agent-based tasks very quickly. High confidence agent-based tasks, just accept. No need to review them. They then spent more time looking at more challenging tasks, right? Documents that needed more care to read, and they spend more time doing this stuff, which then raises questions around productivity, right? if you give more information, more confidence in the system, do you actually improve productivity? People like to do challenging tasks. They're not just doing these tasks to make more money, just doing it because they found them interesting and challenging and tested their abilities. So it raises big questions around this idea that deploying LLMs, for example, will just improve productivity across the board. Recent studies in the UK and the UK government, they deployed Copilot across 12 departments in the UK, various government departments, education, transport, etc., and asked people to use them, use Copilot to transcribe Teams conversations, to generate documents, to summarize documents, etc., etc. And they surveyed all the participants at the end of 3 months, and they found that people use Copilot to do all these tasks in different proportions and saved about 26 minutes per day. The Minister for Science, Lord Valence, was very clear, very keen to point out that this doesn't mean an increase in productivity, right? There are some questions around the methodology used there anyway, in terms of self-reported performance gains, etc., etc. Serious issues around how they did that study, but still, time saved doesn't mean they will do more tasks. Right. Time saved just means maybe they enjoyed using the tool and they will just do something else, use it for their personal stuff, or just go and have another coffee. So all these systems do cost us something, right? All these LLMs cost us a lot of compute, lots of energy. And if it's not improving performance, why are we using them, right? We should really question that. How should we use them to improve performance? So these sorts of studies have been around, lots of research in using confidence information to get people to use them more effectively, to automate more tasks, but do they actually improve performance? Not here. Right. So that leads me to the idea of thinking about the way you conceptualize agent-based systems or AI systems these days, where these systems have more autonomy, they take away control from you, they do tasks on your behalf, and very often, for the last 10 years, this is not a new problem. We have been building autonomous systems of different kinds, robots that can do stuff on their own, but we don't turn on that autonomous mode because we lose control. And I think it's because we've always been building these systems on their own, not thinking about the partnerships we form with them. And I tried to explain this to someone yesterday at a drinks reception. It's like getting married, right? When you're living on your own, you can do anything you want. As soon as you get married, it's not like you can tell your partner what to do. They have their own views on things. And if you have to explain how to manage a partnership, a marriage to someone, it's very different from having to manage the partner on their own. You have to see how they align their preferences, how they align their goals, how they align their interests in certain activities, and whether they trust each other, etc., etc. So testing autonomous systems on their own doesn't make sense to me, right? You need to always think about the partnerships you form, because as soon as you let the machine do stuff for you, maybe you don't learn things. The machine does stuff for you that you unlearn. Maybe you distrust the machine because it can't tell you what it's seeing. It can't tell you in effective ways without overloading you why it's doing certain things, right? They're black box systems. And there are various examples of such human AI partnerships. And what I've tried to, so thinking through all the work I've done prior to this, but what are the dimensions of these human AI partnerships that we need to think about when we design them, when we test, when we build them, when we deploy them, when we govern them? That lens of human AI partnerships is crucial if we want to build systems that we will end up adopting in society. So what are human AI partnerships? Socio-technical systems composed of humans and machines, a bit like human agent collectives. Humans and machines cooperate, coordinate, and compete. But the lens of partnerships makes you think through the feedback loops that you're creating. What do humans learn from what agents are telling them? What do agents learn over time from what humans are telling them? How do they over time start building trusting relationships with each other? And there are many examples of that in the real world. And these systems obviously need to be safe and ethical if we think of them as partnerships. And a lot of examples. And I realized when I show this slide these days that not many people know what these pictures are about. But they're all about human AI partnerships, good and bad, right? This generation of my kids, don't have time to sit and watch a movie, watch a series. They scroll to the next one, scroll to the next one. You don't wait for the next episode next week, right? Which is what we used to do when we were watching these TV series or films. So good partnerships. You've watched Ex Machina or the Fear Index or Space Odyssey. These are machines that turn rogue, that understand us better than we understand ourselves. The Fear Index games the markets, right? Completely crashes everything for its own profit. Ex Machina, an agent decides to get its own freedom, realizes that it's been exploited. And fully understanding, how to manipulate human feelings here in this case. In the Knight Rider, and a really effective human AI partnership, really effective, where the machine knows when the human is in trouble and will come and rescue them, right? Similarly for Star Wars, right? Good and bad examples of human AI partnerships. So I don't like frameworks usually, but I had to build a framework to get people to think about, explain what I mean by, the kind of dimensions of human AI partnerships, the kind of concerns we need to address when we build these human AI partnerships. Thinking about the data that we use to train these systems, the data that they generate, that they use to reason about each other's behaviors and the environment. A key dimension is the design phase. How do we design these systems? How do we think about teaming? How do we orchestrate a human agent team? How do we explain the behavior of these teams? Is really important if we want people to stick with them. And incentives, really understanding human organizational incentives when we design these human AI partnerships. And how are we doing on time? Okay. So in terms of data, and we're starting to see this. I mean, this is prior to LLMs, right? So if you've used Netflix, and now we're seeing this with large language models, you have lots of these positive feedback loops that are being created. So we build these human AI partnerships. They work together for a long period of time. The AI learns what the humans likes and keeps feeding the human with more stuff that looks similar to what they've seen in the past. Don't let them be creative. Doesn't let them learn new stuff. As you will see with your Netflix recommendations, they tend to focus on very specific genres. If you've been watching a certain genre, you get the same stuff over and over again. And when you build these sorts of positive feedback loops, you end up getting oscillations. You end up getting crazy stuff being thrown at you. I think, and that's what we're starting to see with some of these LLMs. When you're starting to feed their data back to them, you start getting bad behaviors and need to refine and retune and relearn certain things. And when you're building agents in the real world, as I mentioned, you need to track who is doing what. And it's really tricky when you're dealing with robots or agents that can make decisions in split seconds, right? So you have humans who are making decisions given the data that agents are feeding them or whatever is going on in the environment is telling them. And you have these complex decision-making chains that can form. For example, this is a team of humans managing a team of drones that are informing a team of humans on the ground, right? It's disaster responsibility. This drone makes a decision on its own using some kind of task allocation algorithm and crashes. But before it crashed, it sent a message to the human saying, oh, maybe, what do you think I should do? Should I crash or should I do X? And the human didn't see that message, right? Doesn't matter. You might have tracked that data, but you've exposed the human to a decision-making point that was really time limited. You had half a second, 5 seconds to react. Was that fair to the human? Maybe not, right? So you should also be tracking what is it that is fair across these decision-making chains. And we see this with autonomous vehicles, right? So when autonomous vehicles hand over control to the driver, it's too late. And they track this in the logs, accident logs that we generate for these AVs. So this is quite important to do. And obviously you have provenance tracking systems, causal reasoning of provenance traces that can help you understand where who might be at fault, why they were at fault, and if you have large provenance traces, it's important to build algorithms to manage that efficiently. In terms of design, just to give you an example of what I mean by design considerations of human AI partnerships. The example I gave earlier of these different human agent teams, you had humans sometimes in control. Sometimes they were tasked by the agents to classify data. So the machine learning algorithm would farm out a bunch of images and ask humans online on some of these crowdsourcing platforms, Amazon Mechanical Turk, or the better ones now to do this, but ask humans to classify these images. So machines in control. In some cases, the human would be tasking a bunch of agents, the drones, for example, to go and do a number of tasks. How many humans do you need? One drone is easy to manage with one pilot. 10 drones, how many pilots do you need if you have a very effective algorithm? So how do you orchestrate these operator-to-machine ratios? So how do you ensure that the system remains effective, efficient, reliable, trustworthy, with small, large numbers of humans, large numbers of machines? And it becomes increasingly difficult then to interpret these behaviors when you're combining human and machine decision-making. So how do you go about doing this? And we built a really effective human-machine team for disaster response through an iterative process. And it always starts with participatory design process, involving the users, involving the ultimate users of the systems, or those who will be impacted by the systems. Taking both quantitative and qualitative approaches to studying the impact of these systems, and in some cases, building digital twins of humans, simulating humans in the system for testing purposes, but always going back to the real world to see how people really react to your system with a proper human-machine interface, and that surfaces the right information without overloading the users. And crucially, to build such systems, what I argue is that you need multidisciplinary teams. And we're seeing some consequences of not having a multidisciplinary team. Many companies building multi-UAV systems, drone technology, Anduril, Shield AI, et cetera, are fundamentally engineering teams, very much driven to build products. They end up building very advanced drones, but put less emphasis on the human-machine teaming elements, which I think is crucial if you want to get these things deployed at scale. And that means bringing in HCI experts, social scientists, cognitive psychologists, etc., to help you build this system so that you understand the human elements. For example, when should you swap out a human when they get tired? Right? Or how do you recognize tiredness in those systems? Or how do you know whether they're overloaded or not? How do you match the machine to their level of skill, etc., etc.? Third dimension I mentioned was incentives, and that comes up, as I mentioned earlier, with the energy storage problem, the grid management problem. You have issues of preference modeling, but when you try to model people's preferences, you may be asking them too much information, so you need to balance that against privacy preservation. There's a cost to asking people for their preferences. You might bore them. And it will be interesting to see what happens with the agentic GPT systems when they try to book your flights and they try to book your hairdresser and just book you to the most expensive restaurants, for example, without you having a say. How do you react to those things? Why? Because you don't want to be bothered by the system all the time, checking with you the price is right. And as I mentioned earlier, when you try to deal with systems of multiple agents and humans who are trying to achieve the best for themselves, self-interested, you need to design incentives so they behave appropriately. And I think we are starting to get to that time again where we need to worry about autonomous behaviors that try to optimize our preferences, but maybe exploiting someone else. Just, I think this morning I read a paper that mentioned that, I think it came out of Stanford University, that mentioned that a number of LLM agents were tested in a number of settings where they were rewarded for giving a product review or some other task, and they would lie to win to win the task, basically. So we need to worry about incentive design, maybe using game theoretic techniques, but also worry about fairness, how these systems result in fair outcomes. Okay, so I'm going to give you a quick example of what we've done in terms of building it out from a multi-agent coordination algorithm into a real-world human agent collaboration team, a human agent team for disaster response. So taking again the problem of allocating emergency responders to various events in a disaster space. In this case, we're looking at humans forming teams in different parts of that disaster space to collect some resources, save some casualties, etc., etc. If you just model this as a simulation of humans and a number of tasks with utilities, travel times to these tasks, etc., you could build a multi-agent Markov decision process. And the version 1 of the system did exactly that, built a multi-agent Markov decision process, and then we overlaid an interface on top for humans to monitor what the agents were doing. And the algorithm would basically send, so if you had all these people in the room, each one of you would get a task to perform. So you would be told, go and do this task with that person over there. And you had only one answer or two answers, okay, or reject the task. I don't want to do this right now. So we built the interface on mobile interfaces, and that was 2015. So whatever phones that you could have at the time, Android phones we were using. For that, we simulated a real-world disaster scenario. So we faked a radioactive cloud over the campus. We assigned roles to individual humans. We told them, okay, you're a medic, you're a firefighter, and you need to do certain tasks because the combination of your skills help you do these tasks better. So we assigned roles to them. We also did the same experiment with real-world emergency responders. So Rescue Global, a charity that works in the UK. So we gave them this app on their phone that would guide them to certain tasks in that fake disaster space. And if they happened to walk into the radioactive cloud, they would get damaged, they would get exposed, and then their counter would go to 0 and they're out of the game. But there was quite a bit of pressure for them to perform. So version 1 tasked the humans to go and do these tasks, and we modeled the whole environment. We could model the radioactive cloud because we knew it from before. We could train our algorithm, our reinforcement learning algorithms on this to help humans allocate tasks, the headquarters to allocate tasks to the best teams. The system failed. System failed because the humans had the option of rejecting tasks, mainly. So we'd keep rejecting until they found a task that they wanted to do with the person they wanted to do it with, ignorant of the cost to everyone else, right? Lots of people lost their lives in that scenario. Lots of things, resources got lost because the humans were not aware of the consequences of their individual actions or had their preferences that they could not expose to a machine. So the algorithm, the MMDP, would not be able to internalize some of these preferences. So we fixed that in 2 ways. So first, the algorithm would learn from the prior data that maybe humans may prefer, from real-time data, as they reject tasks and want to pair with others, we try to learn who they want to work with. And secondly, we move the agent one step away from the end users on the ground. So we created an interface that would ensure that and that was the interface here, would allow headquarters to manage the communication between the humans on the ground and the agent. So agent comes up with a plan, human reviews it, sends it out to the team may reject it, individual people reject it, they say, I don't want to do this task. Human says, why do you don't want to do this task? Then they think twice about not doing the task. They can explain why they didn't want it. Then the headquarters takes this constraint, imposes it on the algorithm, and gets another plan. So there's a mediation process that ensures that the overall plan is effective, is still effective overall, but also accounts for human preferences. In the MMDP, we integrated this rejection probabilities as well. So we did a bunch of algorithmic changes as well as interface changes to manage that human machine team. So it was not just about making the algorithm more effective. It was to do with making the organization more effective, making sure the communication between the humans and the algorithms was properly mediated. And hopefully with LLMs, we can do that more easily now. So if you want to find out more, wrote a bunch of papers, we won a bunch of awards as well for the kind of stuff we're doing at the time. And I think it's even more relevant now with the kind of agents that we have. Okay, so that was the technical part of my talk. If you have any questions now on this stuff, I can try and answer them now. Otherwise, I'll move on to the programs that I'm now working on since I finished it. Any questions, thoughts? Yes.
For these like systems deployed, I mean, you have for
Sorry?
to what extent were these like disasters systems deployed?
So we did a bunch of trials, but bits of that system were used. The crowdsourcing system, some of the algorithms in the crowdsourcing system were used for some events not in the UK, some other earthquake or mapping tasks we had to do, I think following a typhoon in Asia. The human machine teaming elements, we're trying to spin out a company to do that work now. But yeah, it's still ongoing. I think COVID came at the wrong time for us to take that a bunch of things forward, but we're still working on it. Any other thoughts? If not, I can carry on. I don't want to take the full hour and a half. Okay, so a lot of that work that I did led me to win a major grant. The TASK program started in 2020. It was a £33 million program, the biggest one I won. Well, won another one after that, but I'll tell you more in a second. So a big program looking at trustworthy autonomous systems. So how do you build these autonomous systems so we can trust them, we can trust the teams within which they're deployed, et cetera, et cetera. So the task from the funders was to try and orchestrate a network across the UK where individual nodes of that hub and spoke arrangement would focus on different aspects of trust. For example, security, governance, regulation, verifiability, functionality, resilience, et cetera, et cetera. And they were all multidisciplinary teams distributed across the UK. So I ran this for 4 years. It ended earlier this year and generated tons of great work, lots of artistic displays as well as fundamental algorithms and verification processes for machine learning systems. So lots of great outputs. You can find out more on the website das.ac.uk. But following on from that, I won the grant to run Responsible AI UK, which is focused more on responsibility and more on societal implications of AI. And it's a £35 million program that started in 2023. Funds research in the UK, looks to deliver fundamental research, multidisciplinary research into responsible AI technologies, practices, and policy, looks to accelerate the adoption of AI. So we have an accelerator program, for example, in this program that we started this year, plus a bunch of enterprise fellows. We're bringing in research-led expertise to engage with communities, publics, industries, and government. So you can find out more on the website. But this is how we are broadly architected right now. We started 2 years ago, and we've run a number of funding calls. We funded a number of large and small projects, starting with the impact accelerators and international partnerships across the UK. And then funded the big keystones and satellite projects, lots of researchers involved across different disciplines, and also a skills program. So this program was very much constructed from the ground up. So we wanted to see how the communities across the UK understood responsible AI. And we gave them some broad sort of headline challenges. So one of them was around addressing the harms of AI. Another one was around responsible organizations. How do you build organizations that responsibly use, deploy AI and interface with their customers? And third one was around law and AI. And these are the projects that came up following massive funding call, lots of submissions. Each of them are £3.5 million worth. And we're very pleased with them, all led by very talented women. So we have a very diverse team across our AI. Gender balanced perfectly. But yeah, these are the three big projects are led by Maria Yakata at Queen Mary University in London, Simone Stump at Glasgow University, and Marion Oswald at the University of Northumbria. And they address the three layers of what I would call the AI stack. So you have the hard tech. So Maria is looking at LLMs, designing LLMs that involve some level of temporal reasoning. Simone is looking at socio-technical auditing of AI systems, so looking at how they're folded into organizations and how do we then audit their performance and alongside humans. And the third level is really looking at policy and the law when it comes to deploying AI in the criminal justice system, so law enforcement agencies. And it's already having an impact in the UK. So it's produced first guidelines for law enforcement agencies to use facial recognition, for example. And increasingly, we're building new kinds of AI evaluation methodologies within this project. If you are interested in talking to any of these projects, please let me know and I'll connect you. We also have a number of projects within our core research team. We have 20 researchers within the core RAI team. Computer scientists, ethnographers, researchers from the arts and humanities, social scientists in the team. And you can see the breadth of projects that we have, from the hard engineering ones, looking at grid congestion management, to art and AI, understanding how artists are appropriating AI tools, to understanding how we build more effective visual language models, VPR algorithms, etc. I'll just highlight a couple of projects that we've also funded and are continuations from TAS and other projects at Southampton. One of them is looking at using aerial swarms in wildfire suppression. This is a collaboration with UT Austin and a bunch of other universities in the UK, building on the prior work we did in disaster response. So this is looking to build a team of drones that would go and find and extinguish fires in 1,000 square kilometer space in 10 minutes. Very timely research. Well, unfortunately, not timely enough to deal with fires on the West Coast that we saw earlier. But great ambitions to build both the drone technology, the algorithms to farm out those swarms, and to recognize where things are going on. So in my team, we are looking at the human-machine teaming interface to make sure that humans understand what's coming back and how to task the drones in the real world. So this video of the drones dropping this payload here to extinguish a fire. So they built some very, very cool technology there.
Harris multi-agent.
And that's the multi-agent simulator. We've also gone out to build partnerships across the world. So we have quite a large number of collaborators across Southeast Asia, Europe, South America, etc. And in some cases, we go out and actually co-design some of these projects with partners. For example, in India last year, we ran a big sandpit, brought 12 researchers from the UK, 12 researchers from across the IITs in India, and co-developed some projects. And one of them is a technical regulatory sandbox. So looking at how we design laws to regulate AI, to manage AI, and the other one is looking at edge AI. So how do we build effective tools for local communities, rural communities in India to use edge AI applications? Just a brief note on Trace. So this is really looking at addressing the challenge of regulators right now who are trying to cope with evolving AI technologies. And having to formulate regulation that still makes sense. So this is trying to create a sandbox to test both sides, to test the algorithms as well as to trial out different regulations. The other project is off-grid AI, as I mentioned, and we're building some very simple algorithms using VPR. Adarsh is here in the room. He can talk to you about that if you're interested. But trying to track peacocks and peahens in paddy fields across Kerala. We also have projects, skills projects. We have 6 skills projects that are coming to an end just now. One of them, just highlighting here, is looking at AI law and legal training. And that has led to a set of courses on OpenLearn, which is the Open University's training platform. So you can go and get trained in AI and the law, and we funded that. We've also funded 3 enterprise fellows. One of them is Zoe Kurzi at Cambridge University, looking at detecting dementia using AI. Our work goes beyond research and beyond just innovation, but also connecting communities. So we launched our health and care working group last year, and actually running our Champions Day on Friday next week. And we managed to bring together a network of practitioners, researchers from across the health and care sector. So all the NHS trusts in the UK. It's led by practitioners, led by Ian Abbs, who's the CEO of Guy's and St Thomas Hospital in Westminster, and Prokar Dasgupta, who's a urologist. We got the support of the WHO as well in creating that network. And what they are going to do is generate a number of guidance documents and best practice sort of guidance for the health and care sector. And hopefully that will accelerate the adoption of AI in a responsible way. And we have many other similar initiatives, the Ambassadors Council that we've created, which now has Krishnan Ramaya as one of our ambassadors, try and advocate for responsible AI internationally. So that's come to an end on RAI, but if you have any questions about responsible AI UK, I can try and answer them now. But yeah, we're very much open to collaborations. And currently we have a call. So if you have collaborators in the UK, I encourage you to have a look at the website, rai.ac.uk. We have a collaboration grants call, which funds travel, consumables, workshop costs, from 20,000 £20,000 to £50,000. So if you want to spend some time in the UK or host someone here, maybe have a look at that. I can have a chat with you as well after this talk. Yes, Anand.
So in UK, there have been very young guidelines as opposed to regulations. To what extent do you think that they'll move into regulating for trustworthy AI, and also to they look at UAI?
Yeah, so in the UK, they've focused on guidelines and left it to the sector regulators to instantiate regulation for AI. We have we're trying to create a technical authority in the AI Security Institute as well. We have a national physical laboratory that is helping, talking to the regulators to try and help them measure the performance of AI. Still very much at the discussion phase. But the main policy that will be coming out from the UK, or outcome from various discussions, is the AI bill that is coming up early next year. And that supposedly will place the define what is legal and what is not when it comes to deploying AI. We have some worries about that AI bill because they've run a bunch of consultations across various departments, one of them on copyright, which received 11,000 responses from artists, from content creators and research organizations like ours, because they think the UK government is going to water down copyright laws when it comes to AI. So yeah, there are people in government who are keen to accelerate the adoption of AI. In the UK, we have I.AI, incubator.ai, which sits in the Prime Minister's office. And I met with their team last week, and they were telling me that the government just thinks AI is going to solve everything. So they're throwing AI at every single application they can find in the public sector right now. And hopefully something will stick, right? We'll see. We'll see. So I have any other questions on our AI and what's going on in the AI landscape? Because there's tons going on every week. It's hard to keep track. But yeah, in terms of EU AI Act, I mean, if you're following the that strand of AI, I mean, it's clear Europe went ahead with regulating AI heavily, but then realized it's very hard to define what a high-risk AI system is versus a low-risk AI system with a medium-risk AI system. So they issued a consultation a few months ago and asked everyone, what do you think is a high-risk AI system? And we responded, and lots of people responded. And as AI is evolving constantly, it's hard to just pin down, you know, what it is, unless you're talking about safety critical systems, which is very clear. So I have 2 more parts to go. Don't know how you're feeling. If you're feeling tired, just cover the one part, and then we can leave that the other bit for a discussion. But I've been reflecting on what recent advances in AI mean for us researchers. When we see the billions being poured into AI by big tech companies, Scale AI being acquired for, I think, 14.8 billion. Investments in generative AI going to 30 billion, mostly into data centers, but large teams at Meta, at Google and others. And 300 billion in this case in terms of infrastructure. And when we were talking about AI evaluations yesterday at the Book Institution and thinking about the cost of evaluating AI, the cost of building benchmarks, is getting into the low millions, or in some cases millions, to do that. What can we do as research organizations? How do we compete? Right? Can we actually compete when it comes to testing the systems, building better LLMs, benchmarking them? Do we have the resources? In some cases, some universities do have these resources or do get investments from some of these hyperscalers, but most don't. And the questions around what is it that we then focus on as researchers? What is our role if we are not able to build those benchmarks, we're not to build those LLMs ourselves? And many my own researchers would be thinking about, oh well, let's test these LLMs for cultural sensitivity. We know they're not culturally sensitive, but let's write a paper on that and get a paper at Europe. Okay, great. But AI testing is already been done a lot by the markets. Now it's not perfect, right? I'm not saying we should do that, but this is what happened to Google when Gemini failed miserably with some of these culturally and insensitive outputs, or if they're inefficient in some of their compute. DeepSeek showed that you get penalized heavily if you get some things wrong in this market. So the tech companies are very much aware of all the issues and the costs of getting it wrong, whether it's in terms of quality of the outputs, the safety of the outputs, etc., etc. Unfortunately for us, this is not good enough even, right? We're not going to get an ideal outcome for society, and not going to get concrete policies built just by waiting for the markets to react to such things. And it's increasingly hard, right? So industry is responding rapidly, but I think we need to think for ourselves, what is it that we as scientists do now? Do we keep throwing data at these LLMs, ignoring how they were trained, not being able to retrain them, not being able to undertake large-scale tests with 2 million models and Hugging Face to determine which one is the best for the particular task? Maybe we should focus on measurement techniques, on uncertainty modeling, on hardcore mathematical sort of solutions and models of these systems, rather than try to just engineer them out, engineer them to be trustworthy. So lots of questions around the science of these systems, and encouraging results coming out from, I've seen some papers from France, for example, that look at modeling the risk of hallucinations. From INRIA, there's an interesting paper around that. So black box models, how do you predict how can they estimate whether they're hallucinating or not? Right. That's quite helpful for someone who's trying to build a safety critical system out of an LLM. That's one part, one thing to think about, and maybe we can have a chat about that after the talk. The other thing to think about is, what is it that we give to the engineers to fix, and what do we give to the policymakers to fix? Many of us are trying to build safe LLM systems that would not lead to, if you're deploying these systems and they're accessible to 14-year-olds, underage kids, etc., etc., is it our problem or is it someone else's problem? Right? Us as engineers, I'm talking about, or is it the government's problem? And the government should be aware of. We should be able to tell the government that these systems are able to do X, Y, and Z. So we can switch things on, we can switch things off. You tell us, right, what you want us to do. A good example of that is TikTok. We've seen some of these studies of TikTok in China versus the US. Right? In China, you have age restrictions on called Douyin, not TikTok in China. And under 14s are not allowed more than an hour's worth of screen time on this app. The algorithm, which was designed by engineers like us, is controlled by the state, right? They say, okay, you should not allow anything, not use collaborative filtering, for example, to just throw stuff at young kids. And you get very different results, you know, in the US or in the UK. It's the same in the UK. When you download, when you open the app. One example, anecdotal example of how this pans out was in the UK, where they just had a blank phone loaded with a profile of a 14-year-old girl from Manchester. Completely blank, no history, right? The first videos that would be loaded onto the screen would be videos about, you know, and improving the appearance to be more attractive to boys, influencers, self-deprecating stuff, suicidal stuff, as opposed to an app that opens up in China that tells you about educational stuff. You know, they really think about, and people do in government do need to think about this when it comes to the impact of these technologies on the younger generation. Now, how do we want our generation, the next generation of leaders in the country to in terms of their aspirations going forward? So these are serious questions for policymakers, but they do need our help to understand what is it that they can or can't control and how that aligns with laws in the country, human rights, etc. So yeah, it's a debate that we need to have with our policymakers. I have a few other challenges I can mention, but if you have any questions on this, happy to take questions here or reactions to these provocations. Yes.
Question. What parts of the old agent technology do you think can be used to address some of these issues as the LLM-based agents take over? So
Yeah.
what aspects of what has been done to be useful for the LLM folks to incorporate? I know some of them are being incorporated with kind of reasoning, but the specific things as you talked about the human.
Yeah, so one obvious one that comes up when you talk about multi-agent systems is the idea of normative systems. So the environments where these LLM agents would be allowed to operate or where you deploy them would need to meet certain norms, right? So the norms would regulate what the agents can communicate, can share with each other or share with the users. And when they fail, they break certain norms, then they get penalized for it, and these penalties are very obvious to everyone. So there are different tools that have been designed over the years, like electronic institutions. The whole framework is well formalized and well verified. It's out there to be used. Tons of PhDs have been written on this stuff. That's one particular area of work. The other one, which I'm working on, is around multi-agent coordination. So looking at how agents agree on tasks they should share, on meeting scheduling problems or negotiation problems. So there are lots of interesting protocols, negotiation protocols, argumentation protocols that can use, well formalized, well verified, etc., that are to be reused. And not what I worry about is that people wasting a lot of time just having chatbots chatting to each other and hoping something good would come out of it. There are Contra-net protocol is a good one. If you're running auctions for tasks, etc. These are well-designed mechanisms that have guaranteed outcomes or provable, guarantees of some sort, and we should reuse those. But yeah, I'm very excited with the capabilities that LLMs offer us now, because when we were, I don't know if this audience remembers what we were doing back then, when we were designing agents that to talk to each other, we came up with something called the FIPA protocol. The FIPA protocol was a set of speech acts, set of rules around, you could ask an agent to do something, you could give something to an agent, you could share some information with another agent, right? And it was very well-defined protocol. You were only allowed to use these words in certain ways. It was very rigid. And people stopped working on it in 2012, I think. That's it, was gone. Now we have agents that can talk to us in natural language, that can talk to each other using their own language, potentially. And that just makes all these agent-based systems that we designed in the last 20 years more applicable now. We can actually reuse all of this technology with these new agents. What I worry about is also that the understanding of what is an agent right now sounds like we're taking workflows of prompts to call that an agent and to make them sound autonomous when they are not actually autonomous. But there are very well-defined notions of agents around proactiveness and around reactivity, around social ability, and I don't see much work being done around the social elements. So what does it mean to build a multi-agent system or human-machine team right now? Not many sort of fundamental groundings in theory, in mathematics when we come to talk about these systems. Okay. Any other questions? Okay. If you're okay, I can go on, or I can stop here. Up to you. Anyone wants to? If you want me to stop, just tell me. Otherwise, I have 3 more slides or 4 more slides. Okay, so I wanted to share this with you because I shared this kind of talk I give to policymakers. I gave these 4 slides to the Secretary General of the ASEAN last week, to the Minister for Digital for Malaysia last week, and it's kind of concerns that are being seen at regional government level in Asia, in the UK, probably in the US as well. But just to get people to think about the broader implications of the work we do in our computer science labs and other labs at universities. So what we are seeing right now are 3 key emerging challenges in AI innovation: sustainability, sovereignty, and the workforce. I'll give you a few examples of that. I mean, AI obviously consumes a lot of energy. We all know that. There was a big AI and energy summit here, I think, in Pittsburgh a few months ago. We were very worried about how much energy it's going to cost to run this AI, and how the energy will be shared as people are building more generation capacity. Is that energy actually going to serve the local communities where they're being built? An example of how that doesn't work out very well is in Ireland. If you're familiar with data centers in Ireland, you would know that they build all these data centers on the west coast of Ireland so they could game the stock markets in the US. They have the low latency links, and ended up using all the renewable energy that was generated in Ireland. And that meant the local population was priced out of the market. They had to pay for much more expensive non-green energy in Ireland. This is what is likely to happen again. Similarly with water, because many of these water-cooled data centers transition to liquid cooling now, or air-cooled, data centers. They need lots of clean water, just like you need to put very clean water in your car. You need drinking water, drinking level water in these data centers to cool them down. And this is competing with local needs from the normal people. So I guess you've seen this. Vera Rubin, latest GPU rack from NVIDIA. Amazing feat of engineering, can transmit as much data on the web between racks in seconds, 260 terabytes per second. Can anyone tell me how much energy that thing uses? Just one rack, I think that all. So the way I try to, I was talking to a non-expert audience. If I was talking to an expert audience, I would just say 600 kilowatts, and probably people would understand what that means. But even then, I mean, to bring that, to give a better idea of what that means, it's 600 kettles full of water being turned on all at the same time. That's just one rack, and you have hundreds of these racks in one data center. That's 600 kilowatts. That's assuming a 1 kilowatt kettle, obviously. So that's a big problem, and it's going to drain a lot of power from our energy systems. The other big challenge is what we call the job apocalypse. Right, I mentioned the study that we did in the UK around Copilot in various government departments, saving 26 minutes. Not really changing much in terms of productivity. But the bigger worry is around job displacement, where we see a recent research came out of Indeed.com. So if you go on the website, you'll find a research piece on this. 33% of entry-level jobs have just disappeared from the platform. And that's causing this sort of problem, where organizations are changing from being simply pyramidal or triangular to this diamond shape, where you don't have a big funnel to train up your workers. And this is going to cause major problems for lots of organizations. And finally, the trade-offs of sovereignty. So lots of governments are worried about sovereign AI. Jensen Huang is going to all the countries in Southeast Asia, Africa, and telling them you need to have your own sovereign LLM, you need to build your own sovereign data centers, etc., etc. Well, if you do that, like they did in South Korea, you try to have your own data centers and host all your data on your own servers in country, and then suddenly they burn down. Well, that was bad design, right? No redundancy, they lost all access to public services. At the other end of the spectrum, you'll be very familiar with this example, USA got its funding cut, but it had real-world implications for many African countries. They lost access to their electronic health records in Kenya overnight. So where do you hold all this data? Where do you run your LLMs? It is not an easy answer for many of these governments that either don't have the data center capabilities or the ability to build them, and need to rely on investments elsewhere. For example, Singapore. I was in Singapore last week, and Singapore can't build data centers. Just doesn't have the land, right? But it's surrounded by other countries that are competing with it. So where should it build its data centers? What sorts of agreements should it strike with its neighbors? There's big questions for them. And also all these other countries like Malaysia are super energy stressed. So they're trying to double their energy capacity within 5-10 years now. So yeah, serious questions for these countries, which tells me a lot of what we need to do in generative AI, responsible AI, has to be about efficiency, making these systems more efficient, but also advising policymakers on what are the implications of, pushing data out elsewhere or training our own LLMs. What's the benefit of that? Where should we actually focus our energies when it comes to building these systems? On that note, I'll close. So thank you very much for your attention. So if you have any questions, happy to take them now. Otherwise, we can chat over coffee. Thank you.